Okay, folks, here's the second half of the Chapter 10 lecture. Again, you should have the notes that go with Chapter 10 in front of you. This part of Chapter 10 deals with molecular shape, the shape of a molecule based on a Lewis structure. We covered Lewis structures previously. Shape is really important. This has to do with if you have a molecule with, say, 3 atoms surrounding a central atom, does it take on this shape where everything lays flat? So you got your central atom, 3 atoms surrounding it, nice and flat. Or does it take on a shape like this, kind of like a pyramid? Do you see that this is more of a 3-dimensional shape? Do you see how the central atom is not laying flat on the same surface as the surrounding atoms? So that's what this section of Chapter 10 is on. It's called Valence Shell Electron Pair Repulsion Theory, or VSEPR theory for short. No, you're not going to be tested on the name, but when you hear people say VSEPR theory, you'll know what they're talking about. And again, it's all about shape. How important is shape in a molecule? Super important. It's important in everything in the world, in the universe. Imagine you have 2 cars. You have yourself a car that looks like this, with round wheels, or you could have a car with triangular wheels. Obviously, this car with the triangular wheels is not going to function. The one with the round wheels will. Shape determines function. So the shape of a molecule determines how it's going to interact with other molecules, and that's a really important topic. The way we determine the shape around a central atom is again using VSEPR theory, and it's actually pretty easy to use. You start by counting how many electron groups surround a central atom. In our textbook, I believe we call that the steric number. How many electron groups surround a central atom? So let's take a look at a simple Lewis structure. Say the Lewis structure of the carbonate ion, which would be this. So you have yourself a central atom, the carbon. It's surrounded by 3 other atoms. And if you're trying to come up with the steric number, how many things surround that central carbon atom? It would be 3. A double bond counts as 1 thing. A single bond counts as 1 thing. So clearly that carbon atom has a steric number of 3. When you're counting up a steric number, everything counts as 1 thing. A single bond is 1. A double bond is 1 thing. A triple bond is 1. A lone pair is 1. So if you looked at, say, the Lewis structure of ozone, we did ozone in the previous video. You had a double bond to oxygen, a single bond to oxygen, and a lone pair up here. That is the so-called Lewis structure of ozone. What's the steric number? You better say 3. A single bond is 1 thing, a double bond is 1 thing, a lone pair is 1 thing. So you have a steric number of 3. So when you're using VSEPR theory, the first thing you want to do is come up with that steric number. And again, everything counts as 1 thing. Now, based on the number of electron groups around that central atom, you choose one of 3 basic geometries: linear, trigonal planar, or tetrahedral. And to help visualize this, we have a little graphic down below. But to help you visualize this, I have some molecular model pieces. If you had a central atom, pretend that right there is a central atom, and it had a steric number of 2, you would choose this model piece to build your model, because this is clearly a linear arrangement. You would have a bond going here, and this little piece of plastic supports the other bond. So steric number of 2, your arrangement of electron pairs is linear. If your steric number is 3, your electron pairs just naturally arrange themselves in what's called a trigonal planar arrangement. So you'd have one bond here, one bond, or instead of a bond, it could be an electron pair. So one electron group here, one electron group here, one here. If you go to a steric number of 4, at that point it goes three-dimensional. You take on what's called a tetrahedral. This is a tetrahedral arrangement right here. You can see that it's three-dimensional. Can you all see that? That's a three-dimensional object. And they've tried to show you that tetrahedral geometry with this little drawing here. The idea in VSEPR theory is this. Electron groups hate each other. So say I have 2 electron groups, these little green straws are what we use to represent bonds or pairs of electrons. If I have to put 2 electron groups on some central atom, they're not going to hang out next to each other like that. They're going to get as far away from each other as possible because they hate each other. Hence the name of the theory. Valence shell electron pair repulsion. The electron pairs repel each other. If I bring a 3rd electron pair in here, it's going to come in here, and again, because they all hate each other, these will angle down, and you'll get that trigonal planar arrangement. If you have a 4th electron group, 4th electron group comes in, these will all bend down, and you'll have the tetrahedral arrangement. So it's all based on the concept that electron groups hate each other. They stay as far away from each other as possible. So to apply VSEPR theory, again, you count your steric number. Based on that steric number, you select one of these 3 basic arrangements. If you're building the model, that tells you which little thing from your model kit to grab. If your steric number is 4, you're going to grab this to build it. If your steric number is 3, you grab this one. Your steric number is 2, you grab this one. Now, if there's no lone pairs on your molecule, the shape of the molecule is given in this column: linear, trigonal planar, or tetrahedral. Here's the catch with VSEPR theory that sometimes bugs people a little bit. Let's take a look at an example for steric number 3. You could have a steric number of 3, but the shape of the molecule might not be described as trigonal planar. It might be described as angular or bent. What's going on there? Well, if your steric number is 3, and if everything is a bond, everything's going to another atom, like in here. See, that's a central atom, a bond to another atom, a bond, a bond. Oh, in that case, you would say that this molecule is trigonal planar. I hope you can all see why it's called trigonal planar. It's kind of shaped like a triangle. Kind of like a triangle. Everything's flat on the same flat surface, hence planar, trigonal planar. Now, what if you have a steric number of 3, but there's only 2 things that are bonds and 1 thing that happens to be a lone pair? And that would be like this guy here. For the lone pair, we'll just take that straw off. The lone pair, you can visualize as that little plastic thing there ready to make a bond. Well, shoot. That's not the same shape, so you don't give it the same name. You would describe this molecule as being bent. So you got your central atom, and it is bent around the central atom. That's your lone pair right there. And that's what they're trying to show here with the that big rabbit ear with the 2 dots. That is supposed to be the lone pair. So again, for each steric number, you might have several different shapes. You get down to a steric number of 4 here. There's a steric number of 4 where you start with that tetrahedral. Well, if everything's bonding, then like this, you see that everything is a bond to another atom. You describe that shape as tetrahedral. What if you start with that tetrahedral shape, but only 3 of the things are bonding, like this one here? So you have your central atom here, and you have 3 bonds around it, and you have that little dot up top. Oh, that would be this shape here. It's probably maybe easier to see if I do it the sideways. There you go. Can you see it now? It's kind of shaped like a 3-sided pyramid, right? With the little lone pair there. You call that shape trigonal pyramidal. Trigonal because it's 3-sided. Pyramidal because it's shaped like a pyramid. What if you have a steric number of 4, but there's 2 lone pairs? Oh, then it would look like this. Steric number 4 told me I had to start my model building with that little guy with 4 little connectors because the steric number is 4. But only 2 of the things were actually going to another atom, so there's really only 2 bonds, and there are 2 lone pairs. Then you call it angular or bent. So that's vector theory in a nutshell. We're going to practice by working through some examples with you. Real quick, I kind of neglected to mention the bond angles to you, but real quick, anything that's linear, the bond angle, that would be the angle from here to here. That's a 180-degree bond angle. Trigonal planar, your bond angle, the angle here is 120 degrees. Think of it this way, guys. A circle is 360 degrees. You're splitting that circle into thirds, so it's 120 degrees, 120, 120. For your basic tetrahedral here, your bond angle, it's not easy to describe where the number comes from, but it's 109 degrees. So it's 109 degrees between 2 bonds. That one's gone 3-dimensional, so it's not quite like a circle where you can just divide it up. So that's 109 degrees on the tetrahedral angle, which would be this angle here. If you end up taking Chem 1, they're going to go into this in a little bit more detail. They'll definitely want you to pay more attention to those angles. We're probably just going to go for, can you describe the shape? Trigonal, pyramidal, trigonal planar, tetrahedral, angular, bent. That's what we're going to be going for. Okay, let's do some examples, shall we? If you flip the page, I've drawn the Lewis structures for you for these molecules. It says for each Lewis structure, predict the shape, the molecular geometry around the central atom. Well, ozone here, first thing you got to do is come up with the steric number. 1, 2, 3. So your steric number is 3. So if I go to build it, I got to start with that guy. How many of those things are actually bonds going somewhere? Well, you got a double bond and a single bond. I'm not going to try to build the double bond with these little straws. It's too much trouble, but you have a bond off to the right, you have a bond off to the left. That's your model. What do you call that shape? Angular or bent. So this molecule, I usually say bent for these. This one is bent. And The bond angle here, your bond angle here is going to be close to 120 degrees. It's actually going to be a little bit less than 120 degrees. Why is it less than that? Remember the idea here. The electron pairs hate each other. They repel each other. It turns out this lone pair repels more than do bonding pairs. So it's kind of like the lone pair here. That's the stronger of the three groups around the central atom, so it's going to want more room. This lone pair is going to take this angle and constrict it a little bit from the ideal, which is 120. So it's actually going to be less than 120. So you can see from that, even though you might derive this Lewis structure, and this Lewis structure is fine, most chemists will just naturally draw ozone with the bent shape, because we happen to know that when we apply VSEPR theory to it, we come up with bent. So the ozone molecule is indeed bent. It's got more of that shape than this shape, although we left up my lone pair. There we go. Okay, how about carbon dioxide here? For carbon dioxide, what's your steric number? Hopefully you're saying 2. Central atom, 2 electron groups around that central atom. Well, if you got 2 electron groups, when you go to build it, you got to start with that. Right there. And this one's pretty simple. You go to build it. There you go. And what's the shape on that guy? Linear. And the angle here, because it is symmetrical and there's no lone pair, your bond angle, that would be that guy right there. That would be a nice, perfect 180 degrees. And you would describe this as linear. So that one's linear. Next example here. We have our H2S, or hydrogen sulfide. H2S. Okay, steric number here. What's my steric number? Better say 4, because 1, 2, 3, 4 electron groups around that central atom. So when I go to build it, I have to build it based on that tetrahedral shape. Now, 2 of these things are going to get used for bonds. The other 2 will remain as dot dots, just lone pairs. So if I build that, we'll end up with that. Oops. There we go. So there's my sulfur bonded to hydrogen. Sulfur bonded to hydrogen. There's one lone pair. There is the other lone pair. And how do you describe this one? This one is described as being bent. And the bond angle here should be close to 109, but it's going to be a little bit less than 109 degrees. Why is it less than 109? These lone pairs here, these lone pairs push the bonding pairs closer, so those lone pairs will kind of push it, make the molecule constrict a little bit. Sometimes it's only a few degrees. I'll be honest, in the area of molecular recognition, drug design, a few degrees can be huge. It can make the difference between an effective drug or a useless drug. So that's VSEPR theory. We have maybe a couple more examples for you. Let's take a look here. Yep, these 2 are good to do side by side as a compare-contrast. Let me zoom out a little bit. So we're going to look at sulfur trioxide, and we're going to look at the sulfite ion. They're not the same critter. Little bit weird, actually. They look so similar. 1 sulfur, 3 oxygen atoms. 1 sulfur, 3 oxygen atoms. But they're not the same chemical species. What's the difference? Oh, in this arrangement there's 2 extra electrons. Those 2 extra electrons explain the -2 charge. So I've gone ahead and I've drawn the correct Lewis structures for you. The Lewis structure of sulfur trioxide is this. The Lewis structure of the sulfite ion is this, where you have a lone pair sitting on the sulfur atom. I neglected to mention in the previous video on Lewis structures, anytime you're doing the structure for an ion, a charged species, you're supposed to take that ion, when you're done with the Lewis, you're supposed to take it and put little brackets around it and then show the charge. I didn't bother to mention that. I'm not a big stickler for that, but some instructors will go crazy if you don't put the little brackets around it. It's kind of like missing a comma splice in your English class. So again, ions, once you finish the Lewis structure, you're supposed to put a little bracket around it. Okay, so let's get back to VSEPR theory here. For this first one, the sulfur trioxide, what's your steric number? Your steric number there should be 3. 1, 2, 3 electron groups. So when I go to build that, I've got to build it based on this guy, right? That's my central atom right there with 3 little groups around it. I'll put those 3 groups on there. This would be the model. So that would be sulfur connected to oxygen, sulfur to oxygen, sulfur to oxygen. How do you describe that shape? He's flat. He's shaped like a triangle. That is trigonal planar. So you would describe this molecule as being trigonal planar. Nice and flat. And the bond angle here would, because it's so symmetrical, it's going to be a nice perfect 120-degree bond angle. So that's my sulfur trioxide. Now compare that shape with what we get down here for the sulfite ion. Again, the only difference between these 2 species is this one happens to have 2 extra electrons, hence the -2 charge. Those extra electrons, you see, they ended up on the central atom. So if I do my steric number here, my steric number had ought to be what? 4. 1, 2, 3, 4 things on that central atom. So when I go to build this, I've got to build it around that central atom. That's my my central atom with the tetrahedral architecture. So if we slap that guy together, we'll see the shape there. And you see I have the central atom. Here's my central atom. And he's hooked on to, oops, there we go. So there's my central atom. He's bonded to 1, 2, 3 separate atoms here. And you can see it's quite three-dimensional. In fact, it's shaped kind of like a 3-sided pyramid, right? So what do you call this shape? Trigonal pyramidal. He's shaped like a three-sided pyramid. And your bond angle here would be a little bit less than 109. Again, that lone pair is going to make everything else constrict a little bit. So that's VSEPR theory in a nutshell. A little heads up, if you end up taking Chem 1, they show you VSEPR theory all over again, but instead of just having steric numbers of 2, 3, and 4, they'll also have a steric number of 5. See how you got a central atom here connected to 5 different things? So you have a steric number of 5. There's going to be several different shapes associated with this. They'll have a steric number of 6, where you have 6 things hooked onto a central atom. This one's always fun because you can play jacks with this one. And just to show you a couple of the shapes you'll encounter in Chem 1, these won't be on our test or anything, but if you have a central atom with 6 things, and say there's 4 atoms attached, so it'd be this 6-sided thing, or this central atom with 6 attachments, but there's only 4 bonds, you describe this shape as square planar. Square because I hope you can see the outlines of a square there. Planar because all 4 of these atoms here lie on the same flat surface, hence it will be called square planar. Quite a few metal complex ions have square planar geometry. A real famous one is cisplatin, which is a very effective anti-cancer drug that's pretty well known, has that square planar shape. And the reason it works is because of the shape. So again, shape is everything. Now, you get into the fiber, you get some odd shapes. What if you had this thing with 5 places to attach electron groups, and there's only 4 of them that are bonds. You only get 4 bonds. That would be your 1, 2, 3, 4 bonds. And you have the lone pair. They describe this shape as seesaw. If you're wondering, hopefully you can see why it's referred to as seesaw. So if you end up taking Chem 1, the shapes get a little bit more intense than what we're giving you here in the intro class. So that's VSEPR theory. I'm trying to think, is there anything I left out? I think that's basically what you have to know. So given a Lewis structure, be able to predict the shape using valence shell electron pair repulsion theory, or VSEPR theory.